In today's video, I'm going to quickly introduce a very useful tool in digital electronics, which is the logic analyzer. If your interests as a hobbyist lie mainly in the working with digital systems such as microcontrollers, you can definitely afford to buy a cheap logic analyzer from eBay for $10 or maybe a bit more. You can then download free software called PulseView, which is very powerful and open source and allows you to interpret common protocols. In my up-and-coming videos, we'll be looking at counters and the uses they have in modern electronics. Rather than use my oscilloscope to aid our understanding, I'll instead use an affordable logic analyzer so you at home can learn how to use a great tool and give you confidence to use it yourself. In these videos, I'll be using a 24 MHz hobby electronics logic analyzer. I'm not advertising that particular brand, there are loads to choose from on eBay, but I wanted one that's from a manufacturer that wasn't a clone of a major manufacturer. To learn about what they are and how not to use them, let's look at a really bad example circuit of how not to use a logic analyzer. Here I have a 555 A-stable and I'm probing the pins shown. They are pins 7, 2 and 3. If I now capture the outputs on the analyzer, I get the following readouts. Using the cursors we can measure the time period to find the frequency of pin 3, which is the output. We can work out the frequency using the formula 1.44 divided by R1 plus 2R2 times C to work out at 48 Hz is what our A-stable should be reading. However, the analyzer is showing 38.8 Hz. This could in fact just be showing the inaccuracies or the tolerances in our components. If we also check this with the hardware counter on my scope, we can see they're agreeing with each other. However, we should be aware that there can be inaccuracies in the logic analyzer output. Firstly, why can't we rely on the data from pin 2 and pin 7? Well, this is because these pins are actually analog pins, not digital. We can only use a logic analyzer on digital outputs due to the way it deciphers the waveform. Our output should be a valid digital square wave. We should define what a valid digital square wave is. Let's define them as a square wave that swings between VCC and 0 volt with very quick rise and fall times. Let's compare our analyzer output with that of our oscilloscope, probing the same pins. We can see that our logic analyzer is not showing us the full story, but this is our fault. It's user error, not the product's fault. The analyzer works very similar to that of the Schmidt trigger that I discussed in my recent optical counter project. If you haven't seen that video, I recommend it. I will link it below. When you probe a digital waveform, i.e. a square wave, it uses two voltage thresholds to decide if it's a 1 or a 0, high or low, on or off, etc. In a very expensive logic analyzer, you can change these thresholds, but in cheap ones like mine, they're fixed, normally by the buffer used within them. In my case, I believe it is a 748C245, but I haven't opened it up to confirm. Looking at the datasheet, it gives us the thresholds depending on VCC of the chipset power circuitry, not to be confused with the VCC of the circuit under test. For ease of explanation, let's say VCC is 4.5 volts, and we're working at 25 degrees C with their typical values. That means when our signal is over 2.4 volts, it will read as a high, or a 1, for our analyzer, and when it is below 2.1 volts, it will read as a low, or a 0. For our signal to be valid, it should not sit between 2.1 and 2.4, as that compromises our switching thresholds. I have drawn a diagram of a square wave and the analyzer's interpretation below it. I have sloped the transitions to make it easier to see what is happening. We can see that the analyzer only interprets the signal going high once it has reached the high threshold, and vice versa for low threshold, which will result in a small delay. Another issue is the sampling time. The analyzer is not recording the waveform like an oscilloscope, which will be reading it continuously at an incredibly high sample rate, tracking every minor voltage change. Here is a screenshot of the individual samples on my oscilloscope. Look at the timescale. Instead, it only interprets high or low, and the computer screen is merely given a visual representation of this in the shape of a square wave, depending on whether it's 1 or 0 in the code. Please do not confuse this with any sort of waveform analysis and try to work out the rise and fall times. If your sample time is too slow, then the reading may be skewed even more timing-wise. The bottom graph shows the sample time to demonstrate the issue. You can see our signal actually transitions somewhere between our samples, causing an inaccuracy in our measurement. It is worth remembering that you want to sample at least 3 times faster than the signal in order to lessen these inaccuracies. In reality, you want to sample on the highest possible setting. So to summarize, we only use a logic analyzer on digital signals that have acceptable digital square wave. We are not concerned with precision measurements such as rise and fall time slopes, or signal noise or capacitance in the waveform, because it will not interpret this. To look at that, we'll use an oscilloscope. We are mindful that the sample speed is important if you want accurate timings. We are only analysing slow clock speeds with cheap analysers. We cannot view high-speed signals due to the lack of sample speed and probing issues. When you start probing at hundreds of megahertz, the probes themselves will affect the signal through their inductance and capacitance, causing inaccurate results. To probe at these speeds often requires expensive test equipment and extensive knowledge of the field. I hope this has been useful. Please give it a big thumbs up and comment below. Till next time, keep experimenting.